So, last class we are discussing about the solution of H inhibitory control problem, state space formulation framework. So, our plant description is x dot is equal to A x plus B 1 W B 2 U. W is the exogenous input whose dimension m 1 cross 1, and this is the control input whose dimension is m 2 cross 1. And Z is the regulated output whose dimension you can write it P 1 cross 1 and W U are as I mentioned earlier. And Y is your measured output that will be used for control purpose to generate the control U. So, that dimension you can write P cross P 2 cross 1. So, this is the description of the plant. And if you see, we have a two inputs U control input and W is the exogenous input in all equations. So, as we know our, let us call if we have a system x dot is equal to A x plus B u, y is equal to C x plus d u, which we have discussed earlier. Then what is the transfunction of this one? Nothing but from the knowledge of the A B C D matrix, we can write is C S I minus A whole inverse B plus D. When D is equal to 0, the transfer function will be strictly proper transfer functions. And this thing, the transfer function, you see with the knowledge of A, B, C, D, we can find out the transfer function of the system. So, packed notation means in shorthand, we can write G S. If you know the information A, B, C, D, I can easily generate transfer function. It does not mean G S is equal to this one, mind it. G S, if you know the A, B, C, D matrix, I can write this transfer function into this form. So, keeping this thing in mind, then we can write our given set of equation in state space form, we can write in packed form or shorthand form. Our A is this one, as I told you, our input are two inputs are there. If you see earlier equation, that these are the two inputs, one is input control input and another is the exogenous input in all equations. So, this thing if you want to find out the transfer function of this one, we can write in compact form. A, B is combined B 1 and B 2, C is combined C 1 and C 2 and D is all inputs, exogenous input. So, similarly, I can write it transfer function of P of S C, this is our C, you can compare it, this is our S I minus A, this is our B and this is our D. So, if you expand and write it into a matrix transformation form, we will get 4 block like this way. And now, you see these 4 blocks, where the 4 blocks are the, what are the inputs? W and U. W is the exogenous input and U is the control input, and Z is the regulated output, Y is the measured output. So, as we mentioned that this transfer function P f S is nothing but a C S I minus A B plus D, and if you expand this expression and write it into this form, you will get it this C I S I minus A whole inverse then B I plus this one D 1 1, that is our P 1 1 S. Similarly, you can write C 2 S I minus A whole inverse, this is B 1, then B 1 plus D 2 1, and what will be this one? Again, now this column C 1 S I minus A whole inverse B 2 plus D 1 2. Now, this block C 2 S I minus A whole inverse B 2 plus D22. Okay. So, if you just this column, this matrix multiplied by this, then multiplied by this, then add with this one, you will get it this one. In other way, this is nothing but a, if you see this one, this is nothing but a P11S. This is nothing but our P11S. This is nothing but a P12S, and this is nothing but a our P21S, and this is nothing but our P22S. So, in other words, you can say when input is 0, find out the transfer function between W to Z, W to Z when input is 0, and that transfer, this term is not there, and that will be this one what we got it here. Now, similarly, the transfer function between W to Y when U is 0, that transfer function P21 is nothing but a P21 is nothing but a, you see, C2 Si minus 1 inverse B1 plus D2, and that I can write it straight away from the description of that state space equation. If you see the state space equation, that you can write it when input is not there, agree, then one input is now transfer function between W to Z. What is the transfer function? U is not there, this is not there. So, it is A, B, C, D, I can write it simply. When transfer function between W to Z, when U is not there, these two term will not be there, this matrix is A, B, C, D. That is what I am writing for all these cases. Then P12, you see, when W is 0, then what is the transfer function between Z to Y? That transfer function is C1 Si minus A inverse B2 plus this, and that you can write from basic state space description of our plant. From there you can write it. Similarly, I can write it P22S. If you see, I can write it the P22S transfer function between Y to U when W is 0. That transfer function is that one. How can I write it? As I mentioned, from the plant description of this one, from this one I can write transfer function between U and Y when W is 0, this. So, or A, B, C, D, W is 0 means this term will not be there. So, each block, 4 block representation P11, P12, P21, P22, we can find out its transfer function just this way. Now, if somebody interested, because our ultimate aim to reduce the effect of W on measured what is called regulated output, that. So, what is the transfer function between these two things? As you recall, you can recall that our 4 block representation is that 2 inputs, W is the exogenous input, U is the control input, Z is the regulated output, Y is the measured output, which will be used for control purpose. So, this P1 as a, if you see P of S we have like this way P11, P12, P21, P22. So, if you want to find out the transfer function between the W to Z, the lower loop, this is the lower loop of P, this is the lower loop of P is closed with the block P. If you want to find out the transfer function between W to Z transfer function and the K of S in the lower block of P, that is closed, agree, with the block K S, agree. So, how to do it? When you are lower block, so this is the lower block matrices, agree. So, it will be starting with the upper block matrices, you see P11 and it suffixes 11. So, I will start with first suffix. So, what will be P12 S into K of S, this is you have to merge into P block bracket I. Now, P22 S, P11 are already P22 S into Ks whole inverse. So, I have already taken the what is called that first suffix is already taken, or the second suffix I have to take last. First suffix I have to taken first and second suffix I have to take last. So, it will be P21. So, second suffix will be last, this one P21. So, this is the transfer function between this to this of this one. So, our if you look, our statement of the problem is solution of H infinity control problem, standard H infinity control problem means that design a suboptimal control K of S, that this you design a suboptimal control K of S such that our closed loop system, this closed loop system should be internally stable. Not only that, an effect of disturbance on regulated output should be less than some pre-specified positive quantity. So, our goal is this design of suboptimal what is called design of suboptimal H infinity controller means, or standard H infinity controller means design a suboptimal controller K of S such that closed loop system is internally stable, agree, and not only stable, our motivation to design K such that H infinity norm of transfer function between W to Z will be less than some gamma. So, there are two folds in our motivation. They have to design K of S in such a way that it should stabilize the closed loop system internally as well as the H infinity norm between the signal W, exogenous input W and regulated output Z, H infinity norm less than gamma, and gamma is some pre-specified value, positive specified value greater than 0. So, before as I mentioned, as I am now telling you detailed derivation of standard H infinity control problem, we will not discuss derive, only we will give you the algorithmic steps for this one. Before that we have to make some assumptions. The H infinity suboptimal solution is obtained by the following assumptions. The H infinity suboptimal solution is obtained by the following assumption. What is this following assumption? First thing, to obtain a stabilizing controller Ks, to obtain stabilizing controller Ks, the necessary and sufficient condition is this two: A, B2, this pair B2 associated with U in the state equation and C2 associated in the output equation C2. So, our A, B2 must be stabilizable and A, C2 must be detectable. So, these two condition is the necessary and sufficient condition for existence of stabilizing controller. So, this is the first, before we apply the H infinity suboptimal control problem solution of suboptimal, we have to check whether the system is stabilizable or detectable, A, B2 and AC. Next assumption is, because when we will design the H infinity controller, we have to solve two Riccati equation, and the existence of two Riccati equation agree guarantees that this rank must be satisfied. What is the first? A j omega I, B2 associated with a U and C1 in measurement equation matrix C1 and D1 2, and this matrix should have full column for all frequency. Whatever the frequency you say, let us call frequency is 0.1, because I know A, B, B2, C1, D2, find out for particular frequency, find out the rank of this one, and that rank must be full column rank for all frequency. When you will sweep the frequency from 0 to infinity, the rank should not deficiate from full rank, that means n plus m2. This is the A2 one condition, and A3 condition is the rank of A j omega I B1 associated with the exogenous input, C2 is associated with the what is called measured output, and D21 associated with the exogenous input. That rank should be a full row rank for all frequency, means some frequency omega is equal to omega 1, find out the rank. That rank must be n plus m2. Another frequency omega 2, find out the rank of this one, that also must be n plus m2. For all frequencies, this rank should be full row rank. So, this dimension column is n, this column will be how much? M1, okay, and this row is P2, and naturally this one will be n. So, this should be a full row rank. So, A2 and A3 condition ensure that the two Riccati equation which will be necessary to design the H infinity controller, one Riccati equation for designing the controller, another Riccati equation will be necessary for designing a estimator. So, these two existence of solution of these two Riccati equation ensures the rank, row rank, full row rank and full column rank must satisfy. And not only this, the H infinity controller, when you will design it, it will ensure there is no pole 0 cancellation on the imaginary axis, So, this ensure that the system will be internally stable. Okay. So, this is the condition 3, and condition 4 is the rank of D12. D12 associate, if it is the state space description of our original problem, D12 associate with the input in measurement equation, and D21 associate with the output equation in the what is called exogenous input. So, this should be full column, means rank should be M2, and this should be full rank, that means rank of this one will be P. So, this ensures these two condition ensure that whatever the controller you will get it after designing H infinity controller, that controller will be proper, Not only this, you will be able to realize this controller. It will not be improper transfunction of that controller. So, this condition also necessary to be satisfied. So, condition 1 to 4 is essential to design a H infinity controller, standard H infinity controller or suboptimal controller. When you will go to design based on H infinity control approach, then this A to 4, that condition must be satisfied. Other condition is that simplifies our control algorithms. So, A5 conditions, that means fifth condition, this condition is simplifies the H infinity control problem only. So, if B1 D21 dimension is P2 M1, okay. If B1 D21 transpose is equal to 0, physically it implies B1 associated with the noise in the state equation, noise means exogenous input. D21, if you see the D21 is associated with the measurement noise, D21 associated with the measurement noise, though we have considered both are same, that means they are correlated. If this will be 0 when they are uncorrelated, that means process noise and the measurement noise are uncorrelated, then this product of this one will be 0, because this product will come in the H infinity control algorithms. There will, if it is uncorrelated, there itself we can write it B1 D21 transpose, whenever we will get it, we will put it 0. So, from this one I can write it D21 always we can make into this structure 0 I by using that what is called some transformation. I can any D21 I can convert into this structure. Agree? So, if you make it this structure, then D21 D12 transpose is identity from this you see identity. Further implies that B1 D21 if you multiply it by D21 transpose, this into this is 0, this into this is identity matrix this. So, if the structure of D21 is this one, I can write B1 D21 and D21 into D2 transpose is identity and B1 D21 is 0 when process noise and measurement noise are uncorrelated. This is the fifth condition, but that is not the essential to design a H infinity controller. So, sixth condition is again D21 transpose DC1 if it is 0 and D12 associate with the regulated output noise. It is a D12 associate with the regulated output equations and it is associated with the exogenous input. So, if this structure D12 structure if it is 0 I can always make even it is not that structure I can always make it 0 and I structure. If it is this implies D12 transpose D12 is identity matrix and further I can write it D12 C1 D12 that this multiplied by C1 D1 multiplied by C1 this is transpose. Agree? D12 transpose C1 is 0 that is we have seen and D12 transpose D1 is identity. So, this simplification is you can simplify our H infinity standard control problem. This is not the essential what is called assumption that 5 and 6 similarly 7 also. What is 7? D12 is 0. If you see this the D12 is 0 straightway we can see from this equation I will show you this one. If D12 is 0, if this is 0 that means our P11 S is equal to C1 Si minus A whole inverse B1. So, this P11 matrix which is transfer function between W to Z will be strictly proper transfer functions. If D22 is 0, see if D22 is 0 just here that is if D22 is 0 that is then C2 Si minus inverse B2. So, P22 the transfer function between U to Y the transfer function P2 S is your will be strictly proper transfer function. So, these two assumptions D12 0 D22 is 0 is not essential, but if it is 0 P11 S will be strictly proper transfer functions and this is will be strictly proper transfer function P22. If D11 is 0 P11 will be strictly proper transfer function and this will be strictly. This assumption as I told you not needed, but it is simplifies the what is called the solution of Riccati equation other things and also the transfer function between W to Z. So, our main basic assumption A1 to A4 and other assumption 5, 6, 7 is not an essential assumption to design the standard H infinity control problem. So, let us as I told you I will not go for details derivation of the standard H infinity control problem, we will just write the algorithm steps how to design suboptimal H infinity controller K of S. So, our algorithm step for suboptimal H infinity control problem solution. So, first step you write in state space description of the plant into this form. This is a state equation and is x is the state vector whose dimension n cross 1, W is the exogenous input whose dimension m1 cross 1, U is the control input m2 cross 1 and Z is the regulated output and W is exogenous input, U is exogenous, U is the control input, and hence I can find out the dimension of A, B1, B2, C1, D11, D12, and YT is the what is called measured output. Since I know the dimension of W, U and X, I can find out the dimension of C2, D21, D22. This is the first you have to make it into this structure. If you want to design H infinity controller based on state space model approach, then you have to make it in this structure. It is called 4 block representation. It is something like this form: 2 inputs W and another input is U, and this input is your output is Z, regulated output, this output is Y, and we have a controller U we have designed based on this our controller K of S. So, this is our P of S. The 4 block representation you have to write like this way. Next step is that, as I told you, that check the assumption 1, check the assumption 1, A1, A2, A3 are satisfied now. If they are not A2 and A3, this is the corresponding A2 and A3, if it is not satisfied, then what you have to do it? Then you have to modify that our system by introducing the weights. Again, so this, as I mentioned, what is the useful assumption for A1 is what? For A2, A3, for what you are doing? A1 is assumption is that A, B2, A, C2 must be stabilizable and detectable in order to get the controller, stabilizing controller. So, this is the second step, check the all assumption A2, A1, A2, A3. The third is check the assumption A4, A7, though I told you it is not necessary in A4 and A7. You see the A4 and A7 assumption is what it means. The A4, the assumption full rank, column rank, full row rank is used for getting the proper controller. Even if it is not proper, it is a biproper, then hence we can, this will give you the proper what is called transfer function of the controller. Hence, you can realize for A4 and A5, A6, A7. Again, this assumption A4 assumption, check the assumption A4 and A7. A7 assumption is what? A7 assumption D12 is equal to D11 is 0, D22 is 0, means to get this P11, P22 as strictly proper transform, and that does simplifies the algorithm only. So, check, but as I mentioned earlier in our assumption, this assumption, this is our assumption. If you see this our assumption is, this is the assumption is 5, we have considered 0, but this assumption you can relax. This if you see B1, D21, we assigned in assumption 5, 0. So, that assumption you can relax, and this is the assumption 6, if you see that assumption also you can relax it, this assumption. So, I am relaxing that assumptions. Step 4, select a large positive value of gamma, where the H infinity norm will be less than gamma. Gamma is positive quantity, large positive, initially you have considered large positive number of gamma, where gamma interprets is what? The H infinity norm between the exogenous input to the regulated output. Solve 2 Riccati equations. Now, next step is, after checking all these things, you have to solve 2 Riccati equation. What is this 2 Riccati equation? Before I write the 2 Riccati equation in details, that recall our LQG problem or LQR problem. What is this our LQG or LQ? When we are going to design a controller, we have to solve a Riccati equation. This is called algebraic Riccati equation, and this algebraic A transpose P, P A minus P B R inverse B transpose P plus Q, you have to solve it, where you know A, B, R is the designer choice, Q is designer choice. You have to solve P. Once you solve P, you can easily find out the controller gain R inverse B transpose P, the controller gain in R inverse B transpose P. If you want to, once you solve this one, and you see I need the information of A, B, Q, R. Agree? If that Hamiltonian matrix, this is called Hamiltonian matrix, A minus B R inverse B transpose minus Q is the Q is the weightage associated with the state vector, and R is the weightage in the control vector and minus 8. So, this is the Hamiltonian matrix, and from the Hamiltonian matrix I can create what is called the Riccati equation. Once you know the Hamiltonian matrix of this one, I can create the what is called algebraic equation. How would it see? A transpose A transpose P, then transpose of the P A minus P this quantity minus P this quantity B R inverse B, P minus P this quantity, that minus will come, and then P plus Q, whatever the sign is there, plus Q. So, from the, in short, I am writing Riccati of this one means from the knowledge of Hamiltonian matrix, this is nothing but a Hamiltonian matrix. This is nothing but a Hamiltonian matrix. From the knowledge of Hamiltonian matrix, one can create the algebraic Riccati equation. So, keeping this thing in mind, what I am doing it now, I am writing the Riccati equation that we have to solve for the controller. So, now you see the x infinity is the solution of Riccati equation for designing controller. So, this our Riccati equation, this is the Hamiltonian matrix, this is the Hamiltonian matrix, and Riccati equation I can form from the knowledge of Hamiltonian matrix. What is this? This is I can consider in equivalently, you can consider this is A, this is this whole thing equivalently, and this is whole thing equivalently I can consider. If you consider the LQR, then this is nothing but a B R inverse B R inverse. This is equivalent if you consider A, this is whole thing equivalent to B R inverse B transpose, this whole thing equivalently you can consider minus Q, and if you this is A, then it will be A transpose, this whole thing you can minus A transpose. So, I can easily write the Riccati equation A transpose P. So, I am A transpose P means our x infinity, here I have considered the matrix, the solution of Riccati equation is x infinity, A transpose P, then P A, then minus, because minus then what is I am writing P that quantity minus is there here, then P, then this quantity is minus Q plus Q, we have to write it this. So, this is the Riccati equation, and what is the Riccati equation for designing the controller, H infinity controller, designing there for controller part. And what is here is we introduce the new thing that D1 to bar. D1 to bar is D1 transpose D1 to, that is I am consider D1 to bar inverse. Agree? The whole thing is D1 to bar inverse. Now, if you consider the special structure of D1 to as I mentioned earlier, D1 to as I mentioned earlier, if you see that one, anyway, the 0 I 5 just a minute. If you consider D1 structure, you see D1 to transpose D1 to is identity. So, if you that structure, this will be identity again. It does not matter, even if you not that structure, it will be, you will calculate and put the value is here, but it is known to you. So, you have to solve the Riccati equation. We have already discussed how to solve the Riccati equation, different methods that you recall. Once you know the solution of the Riccati equation x infinity, then controller gain k constant controller gain I can use by using that one, and this term will be 0 if this term is 0, if this is 0, then this will not come into the picture in our things. Okay. So, our controller gain is that one. This is 0, if this quantity is 0, then this term will not be there, agree, or you forget it. This will not be 0 if this is 0, that what we have considered in this assumption. If D1 to transpose C1 is 0, then naturally this will not come into the picture, if this is if. So, similarly, that what is called, we can design, this is the controller, this is the your estimator, this is the Riccati, is the estimator Riccati equation. What is the Riccati? And this is the knowledge of A, you again you can consider this is A, this is our minus B R inverse B transpose, then this is our Q, this is our, if it is A, this will be A transpose. So, you can write it, and our D21 is what? That one, and B1 bar expressed by this one. So, D21 bar, if D21 has having a special structure, then this quantity will be identity. Even though it is not a special structure, one can compute by knowing the knowledge of D21. So, from this Hamiltonian matrix, this is nothing but a Hamiltonian matrix, I can write the Riccati equation. What is this? A, I have written A transpose means that matrix only. This whole thing is A transpose means this will go A transpose P, then P A. What is this A will be? That will transpose, I missed it here, P A. Okay. Then P, this matrix is written this matrix into P, because it is minus is there, minus plus Q, that one. So, this is the algebraic Riccati equation, this is you can say algebraic Riccati equation. You have to solve the algebraic equation y infinity of this one, this you know all matrices, then you can solve it, but this is a matrix and nonlinear algebraic equation. So, this is a step 8 is the solution of what is called Riccati equation for estimator, agree, that you have to solve it. Now, step 9 is estimator gain. For estimator or observer gain you have to find out is nothing but that z infinity into k e. What is z infinity? Is related with this expression. I know x infinity, I know y infinity, gamma I have assigned initially very large. So, that z is known, z infinity is known, and k e is what? Y infinity you know, all these matrices you know, you can find out k e, not infinity, k e. So, I can write this is nothing but a estimated gain k l. As you know estimated equation, now estimated equation x hat dot, from basic equation I can write it, from basic equation I can write the estimated equation. You see the our basic equation, see that this is where we basic equation, estimated equation I can write it x hat dot is equal to a hat b 1 w hat plus u 1 w hat plus correction term. So, I am write x hat dot is equal to a hat plus b 1 w hat plus w 2 b 2 u of t plus correction term, and this is the output measurement error is the actual measurement and this is the estimated measurement, that multiplied by what is called estimated gain. This is called estimated gain. So, this is the how is calculated w hat, that this expression in this right hand side everything is known to us from this one, and the y hat, that output estimated value of the output is that one. And if you see this one, our standard what is called LQG problem, where the estimated is there, this term and this term are coming extra in H infinity H infinity controller in comparison with LQG, this term and this term, agree, and this term is coming extra for this one. So, and w hat, you know how to calculate w hat, this one estimated by this. So, I know the estimated equation well defined now. So, I have given the equation number 1 is our, if you see our equation number 1 is the our controller gain control law. This is the equation where u is equal to k c x hat of t equation. This is the estimated equation is 2 and w hat y hat is 3 and 4. So, now one can easily find out the, if you put this, if you put the value of y hat here, w hat here, y hat here, and after that you put u is equal to minus k c x hat in this expression, then I can simplify this equation in final form. So, that is why we are writing the using equation number 1, then 2, 4, in equation 4 we get this expression is nothing but a, if you see you can get this expression by putting the value of y hat by this expression, sorry w hat, and y hat by this expression in this, and u of t you can put minus k c x hat of t in this expression. Then finally, estimated equation, this is the estimated equation, you will get this one. Now, if somebody wants to find out the transfer function of the controller, as you see from the very beginning I have written a transfer function of this controller here, the transfer function of the controller between y to w, y to u. So, one can easily find out that transfer function of this one. Step 11, transfer function from y is the input, u is the output of the controller, input to the controller y, output of the controller u. How will you find out? Using equation 5 and our equation 1, and our equation 1 is what? Is nothing but a u is equal to minus k c x hat of t. This is our equation 1. So, from this one I can easily find out the, this is find out the transfer function k of s. What is, it is something like that, x dot is equal to a x plus b u, y is equal to c x plus d, find out the transfer functions. So, in our case this whole thing will be our a, y of t is the input to the controller. So, this is our b, our output is u of t. So, this will be our c. So, it is c here, b here, agree, and d, there is no d term here, d is 0, d bar, and whole thing is you can think of is a bar, b bar, all these things. So, our controller transfer function, this is the transfer function of the controller. Generally, this controller transfer function will be very large order, even it is more than our original system order. So, one can, if you want, one can find out the transfer function of the controller in this one. Then finally, there exists a stabilizing controller K s if and only if necessary and sufficient condition, two Riccati equation, one Riccati equation for controller, another Riccati equation for the estimator are solvable, and they are solvable provided the assumption which we made it in the beginning of the solution of the problem assumption, that must be satisfied, and following condition is satisfied. That means, rho x infinity y infinity of less than gamma. That means, spectral radius of this matrix, spectral radius means maximum eigenvalue of the matrix, if it is less than gamma square, agree, that condition also must satisfy this condition, and following condition, the following condition must also satisfy, agree. That means, there exists a controller, but that does not mean that controller, what we have designed the controller, that does not mean the H infinity norm of T z w will be minimum, So, what we have to do it? Next is, whatever the initial value of gamma we have selected, decrease the gamma and proceed this whole process, that following repeat the steps 6 and 8. 6 is, then you, when it is you have got the gamma, initially you have the large value of gamma, and we got this solution, let us call this condition you satisfied. Then what we mean, the gamma value we can reduce the gamma value, and then again you solve what you have should solve it, the two Riccati equation, find out the controller gain, observer gain, or the estimated gain, agree, and then again you check these two conditions. If it is less than this one, further you reduce the gamma. In this way process you go on until unless you are able to reduce the value of gamma, agree. So, if this condition is satisfied, that means, and repeat the steps 6 and 8. What is the steps 6 and 8? See, repeat 6 and 8, that this is the 6 and 8, the solution of controller Riccati equation, and 8 is the solution of what is called observer Riccati equation. Once you solve x and y infinity, you can easily find out this. If this is less than that one, then further you reduce and solve x 6 and 8, agree. Step 6 and 8. So, this process will continue until and unless you will be able to reduce the value of gamma, in the sense that when you have solved the two Riccati equation, spectral norm of this two Riccati, product of two Riccati equation, spectral norm should be less than gamma square. If you get it, then further you reduce it. So, finally, I can say compute this, you see this is important, compute the spectral radius of product of these two Riccati equations until satisfactory solution is obtained. Then compute, finally you compute K c, K L, K s s, etc. to design our controller. So, this is the algorithmic steps of that one. Now, let us see basically how you will realize this H infinity controller in block diagram representation. This is the block diagram form. Basically, I am doing, if you see this one, basically I am representing the plant first, then I am representing the estimator, that is all. So, I am just showing you the plant equation, that plant, this is the plant equation that I am just doing first thing, and I made it assumptions that D12, that assumptions anyway. So, this is the equation, the plant descriptions. Plant description is this one. I made an assumption in order to draw the what is called that block diagram form. I made assumption D11 0, D22 0. This indicates that the transfer function P11s and P22s will be strictly proper transfer function. In other words, we made an assumption that our what is assumption number, I think 6, assumption number 6 possibly, yes, 7, sorry. This assumption I made it in order to do this one. So, I made an assumption, assumption 7 is, please see, assumption A7 means assumption 7 is assumed, A7 is assumed. So, if A7 is assumed, that means D11, D12, D11, D22 is 0. So, first you see plant I have represented with a block dotted box. So, what is x dot? Look at the plant description, x dot is equal to Ax. So, A into x plus B1 into W. So, B1, this is B1 W, it is coming signal, then B2 U. So, B2 U, that is x dot, and x dot, and our regulated output Z. Z is what? C1 x, D11 I have considered 0. So, there is no input from W. So, D11 part is 0. Then what will come? D12 U. So, it is coming D12 U, this signal. So, that is the regulated output, and that dimension is, if you consider P1 cross 1. Agree? So, our regulated output, this, and measured output is what? Y? C2 into x, C2 into x plus D21 into what? W, D21 into W, you see D21 into W. So, this is the regulated output. So, this dotted box is the plant description, this is the plant descriptions made it, and in other words I can 4 block representation, I just can make it PS form. Now, it is a estimated equation. If you see the estimated equation here, that is I have just written it, estimated equation. This is the estimated equation, that is I am now representing in block diagram form. Now, you see the estimated equation is what? A, this is the estimated y, y hat. What is y hat? Y hat is a C2 x hat, C2 x hat, and also you see this one C2 x hat, and also that one x hat into gamma square, you see C2 x hat and x C2 x hat, where is C2 x hat? C2 x hat and the gain. See this one estimated equation. I just written all this equation from the basic estimated equation. See, from this equation, putting the W and y hat and u print, I got this block diagram. Agree? This with the dotted things. And controller is what? Kc into x set. Kc into x set is the this is the x set, Kc into x set, and our estimator is a into x set plus B1 into y hat, B1 into w hat, B1 into w hat, w hat below you put it, this is B1 into w hat, agree. Then B2 into u, then B2 into u, you see B2 into u, this block is coming. Then will be correction term. What is correction term? KL into y, y hat, y minus y hat, this is the correction term is coming. So, this, and what is y hat? Y hat is nothing but a your C2 into x set plus D21 into D21 w hat. So, you write it w hat, this one. So, note that this block and this block gamma square D21 B1 transpose x and gamma square B1 B2 transpose, these two blocks are extra term in comparison with LQ. You see this block and this block where you have written here and here are the extra terms in comparison with LQR. This is the HMD standard control problem in structure wise, this one estimator is there and this block is called estimator, this dotted dot is estimator, and that is obtained using equation 2 to 3, this whole block is obtained, this one. So, this is the all about the course. Then I will give you the assignment sheet, and the one problem I will solve, give you the in the assignment sheet how to solve H infinity control problem using MATLAB program, because hand calculation, as I told, manual calculation is just impossible for higher order systems. So, I will work out one example before I give the what is called the assignment sheet. You will find everything in then assignment sheet, how to solve a H infinity control problem for higher dimensional problems. So, this is all about the course, and you will get your assignment sheets from static optimization and dynamic optimization and H infinity control problems, all assignment sheets you will get it in the website. Thank you very much.